Greetings, Math 347 fans. Welcome to this video, second part of a discussion of solutions of homogeneous, constant coefficient, second order differential equations. In our last video, we saw the general construction of such solutions, namely that such an equation always has a fundamental set of solutions defined by two linearly independent solutions that those solutions together as a linear combination forms a general solution. And again, it's a general solution in the sense that that a linear combination, that a member of that two-parameter family can be chosen to satisfy any initial condition. In this video, we're going to have a look at some applications of these second order constant coefficient homogeneous differential equations, and we'll look both in the context of our familiar mass spring system as well as in the context of our RLC circuit. Okay, so to start off, let's have a look at the damped mass spring equation, which we derived the other day using Newton's second law to be mx double prime plus gamma x prime plus kx equals 0. Again, here m and k represent the mass in the spring in the system. Those are positive constants. And gamma represents a damping. You can think of the gamma equals 0 case as being undamped, whereas the gamma positive case is a damped oscillator, or a damped harmonic oscillator. So here, again, we'll take the constant gamma to be non-negative. Okay, so to have a look at this differential equation, we'll start by manipulating it just a little bit, dividing through by a factor of m here to rewrite the differential equation in what you might refer to as second order linear normal form. The coefficient of x double prime is 1. We'll identify that coefficient of x prime to be c, sort of. It's gamma over 2m is c, and omega squared is k over m, and it just turns out that factor of 2 here in our differential equation, x double prime plus 2cx prime plus omega squared x equals 0, is a convenient factor for the eigenvalues. So we know how to solve this sort of equation. We'll try a solution of the form x equals e to the lambda t. We'll find the corresponding characteristic equation, lambda squared plus 2c lambda plus omega squared is 0. And now you can see why this factor of 2 is convenient. It just makes the quadratic equation turn out a little bit cleaner. The eigenvalues lambda are minus c plus or minus the square root of c squared minus omega squared. Okay, so you can sort of see where this is headed. The solution of this system, as you might expect, is going to depend on the form of those eigenvalues, and sometimes you might get real distinct eigenvalues, and sometimes you might get real repeated eigenvalues, and sometimes you might get complex conjugate eigenvalues. So whether you get one of those three cases depends on the relationship between c and omega. And again, here you can sort of think of c as being a placeholder for gamma, so c represents the damping in the system, scaled by 2 times the mass actually, and omega represents somehow the spring constant in the system, right? Again, sort of scaled by the mass in some sense. Okay, so let's go ahead and have a look at the first case. The first case is the case when c is bigger than omega, so you can think of this as somehow there being more damping in the system than spring constant in the system, and in this case we can identify that the roots are real distinct. A fundamental set of solutions includes what I'm calling e to the lambda minus t and e to the plus lambda plus t, right, where those lambda minus and lambda plus correspond to the minus and plus in the square root. And the general solution, again, is a linear combination of those linearly independent solutions, c1 e to the lambda minus t plus c2 e to the lambda plus t. This is our expected two-parameter family of solutions, just like before. And sort of an interesting thing here is that in this case, it turns out that both the lambdas are negative numbers. So that's pretty easy to see for lambda minus, right? Lambda minus is a negative number minus c minus the value under from the square root. But lambda plus is negative also, and you have to think about that a little bit more clearly to identify lambda. Lambda plus is negative, but if you notice that the stuff under the square root is always less than c squared, we can see that lambda plus is minus c plus something that's smaller than c, so it too is negative. Now that's significant because we want to have a look at the long-term behavior of the solution, and in the long term it turns out that this solution always tends to 0. Okay, so comment more about that in the general case in a minute. Okay, let's have a look at the second case. The second case is where c is equal to omega. In this case we have a real repeated root of minus c, and the fundamental set of solutions is e to the minus c, and as we saw last time, t times e to the minus ct. General solution is a linear combination of those linearly independent solutions, and here too the long-term behavior of the system is that it tends to 0 as t goes to infinity. Now, to show that, you have to be a little bit more clever and use L'Hopital's rule. I know you remember L'Hopital's rule, you know it and love it, but in any case, here it is. The long-term behavior of this so-called critically damped case is also that that the solution tends to 0 for any C1 and C2, or you can think of that as any initial conditions. Have a look at the case C less than omega. In the case where C is less than omega, the eigenvalues are a complex conjugate pair. Right? Minus C plus or minus I omega 0. Here I'm calling omega 0 squared the difference between omega squared and C squared, which again is a positive number in this case. Fundamental set of solutions is the exponential times cosine and the exponential times sine. And the general solution is a linear combination of those two linearly independent solutions. Once again, general solution means that it's the desired two-parameter family of solutions that we can use to satisfy any initial condition. Okay, so this problem 2 has the same long-term behavior as the other two, namely that it tends to 0 as t tends to infinity. You have to be a little bit more mathematically savvy here, using the squeeze theorem to show that the exponential dominates over the cosine and over the sine. So I'll omit those details, but that's the long and the short of it, is that that this solution also tends to 0 as t goes to infinity. We'll refer to this as the decaying oscillation. We'll see why it's called a decaying oscillation a little bit later. Sometimes this is also referred to as the underdamped case, right? You can think somehow the spring constant represented by omega is bigger than the damping constant represented by c, an underdamped case. And it's notable again that in the cases, all cases where there's damping, the solution tends to 0 as t goes to infinity. Now that turns out not to be the case when there's no damping. When there's no damping, the purely imaginary eigenvalues are lambda equals plus or minus I omega, and a fundamental set of solutions is of course cosine omega t, sine omega t. General solution is a linear combination of those linearly independent solutions. You can see mathematically that this solution doesn't tend to 0 as t goes to infinity because that limit doesn't exist. There should be a C2 here on this second term, so apologize for that. But in any case, certainly the solution just continues to bounce around, and this is what you would expect again in the case where there is no damping in the system. You expect that the solution ought to just oscillate around. Okay. Go ahead and look at a couple examples of undamped and damped mass spring systems. So here's the first one. Assuming that a mass of 3/10 of a kilogram stretches a spring by 5 centimeters, we'll find the resulting motion if the mass starts 0.5 meters to the right of its equilibrium position from rest. Okay, so we had a look at this mass spring system the other day. We saw that the spring constant K is 58.8 newtons per meter, and if you go ahead and write the initial value problem corresponding to a mass starting 0.5 meters to the right of its equilibrium position from rest, here's that initial value problem, mx double prime plus kx prime, plus kx is 0, where x of 0 is 0.5 and x prime of 0 is 0, right? The initial velocity, or 0, or the mass is starting from rest. We can do what we did a moment ago and divide through by a factor of m to express the differential equation as x double prime plus omega squared x equals 0. Try a solution of the form e to the lambda t and see that e to the lambda t is a solution if lambda is a root of this characteristic equation, the roots of which are purely imaginary, right? So the eigenvalues are lambda equals plus or minus I omega. A fundamental set of solutions given by cosine and sine, and the general solution is a linear combination of those linearly independent solutions, c1 cosine omega t plus c2 sine omega t. Finally, here we go ahead and choose the family member satisfying those initial conditions, x of 0 equals 0.5 and x prime of 0 equals 0. It turns out, and I'll have you just verify this, so go ahead and hit pause right now and run through that on some scratch paper. We'll be right here when you come back. C1 is 0.5 and C2 is 0. If you have a look at omega, it turns out to be 14, and the solution of the initial value problem is 0.5 times cosine of 14t. Okay, so here we see that that solution oscillating with an amplitude of 0.5 and a period just a little bit under 1, right? So the period 2 pi over 14, excuse me, the period just a little bit under 1/2, 2 pi over 14 is just a little bit smaller than 1/2. Okay, a second example of a mass spring system. Here we'll go ahead and look at the same spring constant, but assume that the mass, it should say the mass experiences a damping force of 0.5 newtons at a velocity of 2 meters per second. Okay, so we saw before that the damping constant turns out to be 1/4 of a newton per meter per second. And if we want to identify the resulting motion if the mass starts from its equilibrium position with an initial velocity of 1 meter per second, we'd like to solve the initial value problem mx double prime plus gamma x prime plus kx is 0, where x of 0 is given by 0. Initial position is 0, equilibrium position, and an initial velocity of 1 meter per second, x prime of 0 is 1. We'll do the same thing we did just a moment ago, dividing through by a factor of m, identifying c as gamma over 2m. Of course, omega squared is k over m as it was before. And if you compare c to omega, you find that c is less than omega, giving us this damped oscillation case that we had before. In other words, complex conjugate eigenvalues. So the eigenvalues are a conjugate pair. Lambda equals minus c plus or minus I omega 0, yielding a fundamental set of solutions given by an exponential times a cosine and an exponential times a sine, and the general solution given by the linear combination of those linearly independent solutions. Once again, I won't go through the calculation, but I'll have you verify that the solution satisfying the initial condition has C1 equal to 0 and C2 equal to 1 over omega naught, giving us x of t in the form you see here as 1 over omega naught, that's 13.98, times sine of omega naught t times e to the minus 5/6t. As we saw previously, this is one of those solutions where you can think of it as an oscillatory function with a time-dependent amplitude. And here you see that time-dependent amplitude, 1 over 13.98 times the exponential is the dashed line. And then, of course, the blue line is the oscillatory part times that time-dependent amplitude. So the envelope of solutions there formed by 1 over omega naught times e to the minus 5/6t, and the solution itself in blue. Okay, a couple comments about more general case of these solutions. We've seen that oftentimes we run into solutions of the form c1 cosine of beta t plus c2 sine of beta t. In other words, a linear combination of cosines and sines. This comes up in the undamped case as well as the damped oscillation case. It turns out that you can always rewrite this linear combination of cosines and sines as some constant a times a single cosine with a phase shift, with a shift phi. So we're sort of replacing the constants c1 and c2 by the constants a and phi here. And the trick is to let the constant a be the square root of the sum of those constants c1 and c2 squared. In this case, multiplying and dividing by a gives us this form for the linear combination of cosine and sine. Here I've written a out front of the parentheses and then just expressed a in the denominator there as the square root instead. And to see why this is convenient, I'll go ahead and identify a triangle that corresponds to having legs, or right triangle with legs c1 and c2. Okay, so here's that triangle. One of the legs is going to be given by c1 here. One of the legs is going to be given by c2 here. And I think you'll agree that being a right triangle, the hypotenuse is the square root of the sum of those things squared. So if you stare at this triangle long enough, which I encourage you to do, again, go ahead and just press pause now, you'll find that the coefficient of the cosine term looks like adjacent over hypotenuse, or another cosine, and the coefficient of the sine term looks like opposite over hypotenuse, or another sine, as long as you identify the angle phi correctly. So here I'll identify that angle phi to be the angle adjacent to C1, and we can go ahead and write the coefficient of the cosine beta t as a cosine of phi, the coefficient of sine beta t as sine of phi, and a really old trigonometric identity that you may not remember, that you used once and probably forgot, is that that linear combination of cosines and sines, it can actually be written as the single cosine of a difference. So here we'll go ahead and identify the phase amplitude form, again as cosine beta t minus phi times the amplitude a. And again, this will be sort of convenient for us to be able to identify the amplitude as well as the envelope of solutions in the damped oscillatory case. Okay, so a little bit of terminology here. Again, the constant out front a is called the amplitude of the oscillation. The phase phi is given by the inverse tangent of c2 over c1. Now you have to be a little bit careful with the quadrant. It turns out that the range of the arctangent function is only from minus pi over 2 to pi over 2. You probably remember that from Math 162. So that the phi that you get by itself is only in the fourth or the first quadrant. Now, of course, we may want to have a phi that's in the second or third quadrant, depending on the SIGN signs of the sine and cosine term in front of the phi. So you have to adjust that a little bit carefully sometimes. Phi over beta turns out to be the phase shift. You can think of that as a shift on the t-axis. We call beta the natural frequency, and capital T 2 pi over beta is the period of the corresponding oscillation. So go ahead and have a look at an example, a couple examples actually, using this phase amplitude form. These will both be RLC circuits. So here's an LC circuit. If you have an LC circuit, you can think of the resistance as being 0, or analogy of an undamped system. So go ahead and divide through by the inductance L, and express this as I double prime plus omega squared I equals 0, where omega squared is given by 1 over LC. And of course the initial conditions here are just given as the current at 0 is 1, and the derivative of the current at 0 is also 1. Okay, so we know how to solve this problem. We can try a solution of the form e to the lambda t, see that solution e to the lambda t requires that lambda be a root of the corresponding characteristic equation, and of course those roots are purely imaginary. The eigenvalues are purely imaginary in this case. This gives us a fundamental set of solutions, cosine omega t, sine omega t, and I'll just go ahead and have you verify that the solution of the corresponding initial value problem has C1 equals 1 and C2 equals 1 over omega, giving us a solution that's a linear combination of cosine and sine in the special form. Okay, so to express this in phase-amplitude form, I'll go ahead and first substitute in omega equals 1 over square root 10, and then identify the amplitude A, again, as the square root of the sum of those coefficients of cosine and sine squared. Okay, so here's A, the square root of 11, right? That's the square root of 1 squared plus the root of 10 squared. So we know how to change this into phase-amplitude form with a cosine of t over root 10 minus that phase phi, which we can identify to be the arctan of 10, and it turns out that when phi is arctan of 10, that the phase shift is about 4 seconds. So once again, you can think of that phase shift as a shift on the t-axis when you have a look at the oscillation here. So the graph of the solution looks like this. You can see that shifted cosine shifted by about 4 seconds, and the amplitude a little bit bigger than 3, right? That's the square root of 11 for the amplitude. Okay, wrap up with one more example of an initial value problem that you can think of as a damped mass spring system. Here, x double prime plus 2x prime plus 5x is 0, where x of 1 is 3 and x prime of 0 is 3. So I think I misspoke there. X of 0 is 1, x prime of 0 is 3. Again, you can think of this as a damped mass spring system where the mass is given by 1, the spring constant is given by 5, and the damping constant is given by 2, displaced by 1 unit and given an initial velocity of 3 units. Okay, so I won't go through the solution in gory detail, but I'll go ahead and outline what you would do. The trial solution e to the lambda t leads to complex conjugate eigenvalues. Those eigenvalues turn out to be lambda equals -1 plus or minus 2i. Fundamental set of solutions given by the exponential times the cosine and the exponential times the sine. And from that fundamental set of solutions, we can identify the general solution as a linear combination of those two linearly independent solutions. Finally, we can show that the solution to the initial value problem has C1 equal to 1 and C2 equal to 2. Okay, so here is that solution to the initial value problem with C1 equal to 1 and C2 equal to 2, from which we can express the linear combination of cosine and sine as the square root of 5 times the cosine of 2t minus phi, where again phi is given by the arctangent of 2. Okay, 1.11 radians. The phase shift turns out to be about a half a second. So here we can use this form to identify the envelope of solutions. So here's that envelope of solutions, root 5 times e to the minus t, and also the oscillatory part in between, given by that root 5 times the exponential times the cosine. Okay, that's it for applications of these homogeneous constant coefficient second order differential equations. Hope you've enjoyed this video. We talked about the overdamped case, the critically damped case, the damped oscillation, as well as the purely oscillatory solution corresponding to the eigenvalues. Did a couple examples and then saw how that linear combination of cosine and sine can always be written in this phase-amplitude form, where the phase is given by the arctangent and the amplitude is given by the square root of the sum of a couple of squares. Hope you've enjoyed this video. So long for now. We'll see you next time.